All right, so we are doing your favorite thing from a few chapters ago, curve sketching. Yay! And I remember when you guys were like, oh man, I don't know how to do this, but I'm just going to skip that question on the test. Yeah, it's back to haunt you. It's Halloween. It's funny. Okay. Anyway, it's back to haunt you a little bit. No, we need to do a little bit of curve sketching, but before we only had a few tools. Now we have more tools in our toolbox to be able to sketch these curves better. So the first thing we want to do is look at our curve sketching recipe, and you remember most of this from a couple chapters ago. So you see these things right here that I labeled pre-calc. These are things that you could do without calculus. These were things that we did earlier to sketch our graph. We gave the domain, we reduced it, find vertical asymptotes and holes, we give the x and y intercepts, we find the end behavior, which is limits, and then we check for symmetry. Now with calculus, we have new tools that we add. So we do all of that stuff first, and then we add, we find the increasing and decreasing intervals and relative extrema, we find concavity and points of inflection, and then we graph. So let's see what it looks like. So here's a rational function right here, and let's just get started. So the domain, what's the domain of this one? Well, remember, domain restrictions exist anywhere where we do anything illegal in math, right? And the two things that are illegal are dividing by 0 and taking the square root of a negative number. So we look at this and we say, okay, are we ever taking the square root of a negative number? No, because there's no square roots. Then the second thing is, can we ever divide by 0? No, because that denominator is x squared plus 1. There's not a single number out there that you could put in here for it to equal 0. And if you tried to solve it, you would see that it equals x squared equals negative 1. And there's not a single number in the real numbers that when you square it equals negative 1. So the domain of this function is all real numbers. So then it doesn't have any vertical asymptotes or any holes because those are both domain restrictions. So you'd only have those if you have domain restrictions. Now we got to look for the x-intercept. Remember, the x-intercept is where y equals 0. So where does y equal 0? Well, we can just set this equal to 0. 0 equals 2x cubed over x squared plus 1. And if we started trying to solve this, we'd notice that like when we multiply this over here, we just get 0 because think about this, when you have a fraction, does it matter what's on the bottom if 0 is on the top? No, the only way to make a fraction 0 is to have 0 on the top. So you can have a million on the bottom, it doesn't matter. If there's 0 on the top, then the fraction is equal to 0. So we need to figure out where is our numerator equal to 0. Well, when x equals 0, our whole fraction is equal to 0. So for this one, our intercept is 0, 0, because y is equal to 0 when the numerator is equal to 0, the numerator is equal to 0 when x equals 0. Okay, so then our y-intercept, that's where x equals 0, and that's also 0, 0, because we can just plug 0 in for x, and it spits out 0, 0. So then our end behavior, remember these are limits. So the limit as x approaches negative infinity of f of x, and the limit as x approaches infinity of f of x. All right, so what is this doing as it approaches infinity? Well, really what we have here is 2x cubed over x squared, right? And so when I put huge numbers in here, this behaves basically like 2x, right? Because x cubed divided by x squared is just x. What happens when I put a hugely negative number in 2x? Well, I get out a hugely negative number, so that equals negative infinity. What happens when I put a hugely positive number in there? I get out positive infinity. So the end behavior is the limit as x approaches negative infinity, it goes to negative infinity, and as it approaches positive infinity, it goes to positive infinity. And so that basically means we know it's going to do something like this, we just don't know exactly what it looks like yet. Then symmetry, we check, and remember we put in a number then we put in the negative of that same number and see what we get out. So if I put in 1, what do I get out? I get 2 over 2, which is 1. So when I put in 1, I get out 1. When I put in negative 1, I get negative 2 on top and positive 2 on bottom, so I get out negative 1. So that tells me that this has origin symmetry. All right, now we're into the calculus. So we're looking at relative max and relative min. Now remember, this has to do with the first derivative. That's why I wrote f prime right there. So this is the first derivative. So the first thing we're going to do is find some critical numbers. So what are our possible candidates for critical numbers? Well, we have, I'll rewrite it here, f prime of x equals 2x squared times x squared plus 3 over x squared plus 1 squared. Ooh, okay, so our critical numbers are anywhere where this derivative is equal to 0 or anywhere where it's undefined. Right? Those are our critical numbers. So let's see. Our possible candidates, it would be equal to 0 when x equals 0. And then if you look at this one, okay, so this, if x equals 0, the whole thing is 0. Can this term ever be equal to 0? No, because if you took any number, it doesn't matter what it is, and you square it, it becomes positive, and then when you add 3 to it, it's still positive. There's no way to get to 0. So our only number that makes this function 0 is 0. So our critical numbers, f prime of x equals 0 at x equals 0. And then it would also be where it's undefined, and that would be where the denominator is equal to 0. Is this one ever equal to 0? No. So our only critical number on this one is 0, 0. So then we have to decide if that's a min or a max. So this is where we do our f prime number line. I'm going to get a regular tune on that, so it's not like a different tune every time. All right, 0. This is our f prime number line. What's going on with f prime? Okay, so let's figure out. If I put a number smaller than 1, or than 0 in here, what is it? All right, so if I put numbers smaller than 0, like negative 1, into my derivative, what's going on? Remember, this is my f prime number line, which means I'm looking at f prime. What's going on with f prime, okay? If I put negative 1 into the function, I get out 2, I get positive times a positive over a positive, so that's positive. If I put in positive 1, I get positive times positive over positive, so it's positive. Aw, man! So this critical point isn't anything. So this is a monotonic function. It means it's always increasing, right? This positive right here tells me that it's increasing, and this tells me it's increasing, so it's constantly increasing. So is there a relative max? None. Is there a relative min? None. And now we got to check for possible points of inflection. So PPIs or PIPs, pips. So our pips, what we do is we find where is the second derivative undefined or equal to 0. So I'm going to give myself some extra room down here. So we are going to figure out where the second derivative is equal, undefined or 0. Okay, so it's equal to 0 at when the numerator is equal to 0. F double prime x is equal to 0 when negative 4x x squared minus 3 equals 0. So that's at x equals 0, because this term would be equal to 0 when x equals 0. And then it's also at x equals the square root of 3 plus or minus, because that's when this term is equal to 0. And so these are our possible points of inflection. These are our pips. So we do an f double prime number line with these numbers on it. Okay, and then we see what's going on with the function at each of these spots. Well, if we go to -2, put -2 into my second derivative. Oh, I forgot to check if it was undefined. It's not undefined because the numerator is, or the denominator is never equal to 0. So that would be our other pip, but it's not. So, okay, so if I put, say, -2 in here, because that would be over here. If I put -2 in there, I get out a positive value. If I put in -1, I get out a negative value. If I put in +1, I get out positive, and if I put in like 2, I get out a negative. So these were all my possible points of inflection. Now what I found is that this is concave up, f of x. It's concave up, concave down, concave up, concave down. So these are points of inflection, okay? So when x equals -√3, when x equals 0, and when x equals √3, I change concavity. And if we plug these in, we would find that it's -3√3/2, and then +3√3/2. Okay, so now we have a lot of information, and we just have to do this sketch. Okay, so we know the domain is all real numbers. That's important because if you end with a sketch that looks like this, that you have a domain of all real numbers, that sketch doesn't follow that pattern, right? It doesn't go to all real numbers. All right, so we have no vertical asymptotes. We have an x-intercept and a y-intercept of 0, so we put a point there. We know that as it goes to infinity and negative infinity goes up, up, and there's the bell. All right, so we have a point of inflection. Let's see here and here. So we know that it's like concave up, concave down, concave down, concave up. So there you go. That's our sketch. Catch you later. If I can stop it. It's not letting me stop.